So, quiz, mark your own. So this is on, the first quiz that I gave you before spring break was on point charges. This is on parallel plates. Given the following pair of parallel plates, what's the magnitude of the electric field? Okay, electric field, symbol capital E, is the voltage divided by the distance. By the way, in your review and on your test, because they often give us as a multiple choice question, you'll notice they often give you that distance there as well, just to screw you up, because they have to give you legitimate wrong answers, so don't fall for that. It's the distance between the plates. It's going to be 0.055. Hang on, Mr. Dewick, that's the distance. Let's put that on the bottom, Mr. Dewick. Let's try that again. 0.055. It is meters, yes. And the voltage, careful, it's not 500. The voltage, I think, is 750, because you're going from negative 250 to positive 500. And 750 divided by 0.055, or 5.5 centimeters. Looks like the electric field is about 13,600. Units, volts per meter, or newtons per coulomb. B. Suppose an electron is placed right at location A at the bottom of the diagram. Oh, direction, thank you. Comma, so 1 mark for the magnitude, thank you. Direction, which way would a positive want to move if it could? Down. So we'll go 1 mark for that, 1 mark for that. By the way, which way would an electron want to move then? Up. So if we put an electron right there, what will its final speed be at the top? It wants to fall. It wants to fall up. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. We have initial kinetic, initial potential equals final kinetic. Final potential. It's starting out at rest. Initially, it has potential energy. That's why it's going to fall. But when it hits the far end, it's like it's hit the ground. Its potential energy is now 0. I'm going to have a half mv final squared. And we said that between parallel plates, the potential energy could be given by qv. They want the final speed. I think the final speed looks like it's going to be 2qv divided by m square root. It's going to be the square root of 2q. It's an electron. 1.6 times 10 to the negative 19. Voltage, 750. Divided by mass. It's an electron. It's on your formula sheet. 9.11 times 10 to the negative 31. Yeah, I'm going from memory. It is. Woo! Wow, I can't believe I pulled that one after spring break. 2 times 1.6. Try that again, Mr. Dewick. 1.6 times 10 to the negative 19 times 750 volts divided by 9.11 times 10 to the negative 31. What the? That's faster than... Oh, square root. That's faster than light. That's a problem. Square root. And I get 1.62 times 10 to the... Is it 7th? I think it was. Let me double check. 1, 2, 3, 4, 5, 6, 7 meters per second. In terms of marks, I would probably go something like this. I think I would give you 1 mark if I saw that, 1 mark if I saw that, 1 mark if I saw that, and then 1 mark for the final answer. But if you got it right, I'd give you 4 out of 4. Turn the page. Suppose an electron, it's an electron, is traveling at an initial speed of that. It enters an area between 2 parallel plates where the potential difference is shown below. What will its final speed be? So I guess because this is positive, it's going to speed up. And then once it leaves the plates, it'll keep going at a constant speed. maybe we, now someone at the tutorial said, hey, Mr. Duick, wouldn't it slow down and want to get sucked back to the positive? Hey, maybe we got some kind of an insulator here. Maybe there's no electric field getting out, or maybe I'm just in my imaginary physics world giving you a nice little question. Is there a change in height? Is there a change in speed? This is a job for conservation of energy. Are any of these zero? Once it leaves the plates, that's like it's, you know what, this is like dropping an object and it hitting the ground, except imagine there's a hole dug in the ground so it can keep falling. Oh, but Taylor, it's not going to speed up when it keeps falling for some dumb reason, so my gravity analogy breaks down eventually. That's what we're really kind of talking about. So when it hits this section right here, it's now out of potential energy because it's hit the ground, so to speak. You know, I'm going to wimp out, I think, and go, because it's lots of typing and number crunching. Physics 12. Yep, I don't want gravitation. I don't want that open either. Electrostatics. That was quiz number 2. Answers. Answers. There we go. I need answers. So, crunching the numbers, we have a half mass, it's an electron. Initial speed, potential energy is QV, so electron times 150 equals a half mv squared. I crunched all this and got an answer, and then I divided by a half and divided by the mass to get V final, and then squared square root. So I think you get 7.26 times 10 to the 6 meters per second? Yes? So, can you give yourself a lovely score, I guess, out of, count 'em, 13? So, I had been asked if we look at the ultimate electrostatics assignment review. Usually during the tutorials after school, I do my I like this question routine. However, since I wasn't recording yesterday's session because my tablet was Kaputski, I'll do it right now. You know what I need to do first, temporarily? Pause my... All right. Questions I like. Number 1, you need to know how the electric field between parallel plates works. Number 3. Or you could just write them down on a piece of paper. I don't know. Now, number 6, this expects you to actually know circuit diagrams, which we just started to do now. This is a great question for the end of the year because it combines a circuit diagram along with electrostatics, but it did tell you this is the positive end, so you hopefully clued in that this is the positive side, this is the negative side, and so you can tell which direction the electric field is. But you need to know how to figure out the direction in electric, very similar to the quiz we did today, the direction in an electric field between parallel plates as well. You also need to know, again, the idea that the electric field between parallel plates is uniform. So in number 1, it's not only that they're all in the same direction, but they should all be the same distance apart as well. Because how close the lines are or how far apart they are shows their relative strength. If you saw all of a sudden a couple lines were further apart, that would be a wrong answer as well. Oh, except on the very, very ends, you can see there is a bit of curvature to the electric field. This is why the old style TVs didn't quite have a great picture, because you always had a bit of blur. HD works totally different. Google if you're bored and find out. I love number 7. Okay, so number 7, I'm asking you for the electric potential. Energy? Energy? No, voltage. I would also have no problem giving you that same diagram and saying find the electric field right there. I would also have no problem giving you a point charge right there. So right now I just gave you the location, putting a charge there, say find the net force, all the ways I can mix and match, or find the overall energy if I put a charge right there. 10. Totally number 12. I like number 12. I like number 12. I like number 13 conceptually. I like number 14. Again, there's an electric field with two charges. Same as number 12, except in this case, instead of between the two charges, we're to the left of the two charges. But if you haven't clued in yet, you're going to have a question on your test where I give you two charges and a location somewhere between them, or to the left or to the right, and I say find the net electric field, magnitude, and direction. 16. 17. 20. 21, got to be able to recognize an electric field diagram of some type. 22. 22 that's almost the same question. It's almost exactly the same question we did on our quiz, except because even the distance is 0.055, it's 700 volts instead of 750 volts. Apparently I had that in mind when I made up that question. 23, electric field, yeah. Oh, this is nice, electric field and electric potential, so asking you to figure out which one's which. You know what, that might make a nice part A and part B for a written question. Or I could do it as one multiple choice. 24 is good. 25 is good. So I'm not going to ask you about the cathode ray tube on this test because my introduction to the cathode ray tube, how a TV works, they didn't actually work that way. Instead of bending the electric beam, instead of bending the electron beam using parallel plates, because the plates have to be long and they want it to miniaturize, they found a much better way. We actually bend them using magnetic fields. So we're going to revisit the cathode ray tube in a couple of units properly, and then I'll say it's fair game to ask you conceptual questions about it on the test. 27, this is a nastier electric field because they're not in a nice straight line. You have to add them together tip to tail. This would be fair game as a multiple choice, but I'm not going to give you one like this as a written. 28's fair game. 30. 33. 35. They're kind of getting repetitive. Like yet again, we have two charges and a location, and we're finding the electric field, magnitude and direction. Sure, B is fine too. If the charge experiences a force to the right, you can figure out whether it's negative or positive based on the direction of the electric field. If the electric field is to the right and the charge feels a force to the right, then it must be positive because the electric field was defined as which way would a positive want to go if it could. Magnitude, you can probably do some cross multiplying and figure out how big it has to be. 36 for recognizing a diagram. 37, yet again, two chart, Cathode ray tube, I said I'm not going to hammer you this time. 39. 40, 41, 43, so on your test, 43 is, again, our standard 2 diagram. This time, though, instead of saying find the voltage there, I'm telling you the voltage and saying find the mystery charge. I will, specifically in the multiple choice question, there are a couple of questions where instead of saying find the answer, I give you the answer and I say work your way backwards and find either the distance or the missing charge or I guess that's really all that's ever showed up in our formulas, really. The charge or the radius or the distance. Anyways, so be prepared to set everything up. But I figure asking you to solve for anything is fair game once you have the initial setup, right? Cathode ray tube, cool, but no. 46. Yeah, 47 again. I mean, clue in. Apparently that showed up about 10 times, so Any of the scholarship ones fair game? Probably 52. I mean, that's nasty, but let me see. Hang on. 2 protons, so we got 2 charges. I give you the distance. I didn't give you the diagram. If they're both initially at rest and then one is released, what's the final speed of the released proton with respect to the fixed? So final speed, I guess that means it's getting out to the edge of infinity, so its final potential energy must be 0. Yeah, you know what? If I'd given you a diagram, I would totally consider that fair game. Without the diagram, oh, and the fact that you got to clue in, it's a proton, you have to know the charge. Oh, I don't know the mass. It's a proton that's on your sheet somewhere. But I would actually consider 52 not that bad a question. I'm a little surprised that was a scholarship back in the day. So there's your hints. Last day, we looked at basic circuit concepts. Basic circuit concepts. Lesson 2. Any questions from the homework you want me to go over? Now is your chance to ask. And I'll understand if you didn't do the homework because for some reason you're cramming or studying or you had a chem test. Please, rather than not doing it, I have no problem on Wednesday when I continue on with circuitry if someone says, hey, Mr. Dewick, from lesson 2 or lesson 1, I have no problem doing that. I have less of a problem doing that than someone just saying, I feel too embarrassed to ask because I'm cramming the homework. But by Wednesday, be back on track, please. This is why the 2-week spring break, I'm not a big fan of it, despite the fact that the time off is nice. Any of these that you were going, So, sorry, can I do 7? So it looks like the amount of energy is 10 kilojoules, 10,000 joules. Do you mind if I just go straight to that? And they told me that the resistance is 30 ohms. They told me the voltage is 120. They want me to find time. Well, I think what I'm going to jump at is that power equals work or energy divided by time. Because that's the equation that has time in it, that has some of this stuff. Problem is, I don't know the power. Oh, wait. Remember I said yesterday, if I know any 2, I know 4. I do have an equation for power. This is going to drive me crazy if I have to do this every time, but apparently I do. Power, I think, was V squared over R. Wasn't that one of our versions of the power law that had voltage and resistance in it when I plugged the one into there? Going from memory, I think it was V squared over R. I could rederive it if I had to. Do you know V? Yeah. Do you know R? Yeah. Do you know E? Yep. I think we can solve for T. I think time is going to be the energy times the resistance divided by V squared, I hope. I never signed this question until this year, but it was apparently just before lunch and I was hungry because I saw a hot dog. 10,000 times 30. I thought you gave lots of thought to what you give us, Mr. Dewick, and really think things through. Who knows? 20.8 seconds. Hey, that looks perfect. There you go. Here's the good news, here's the bad news. If you ask me to pick the single most important lesson for this unit, it's today. Now, I will be flogging part 2 of it on Wednesday, so that's good. But if you get today, everything that I do for the remainder of this unit should not be a surprise, John. It should be more a feeling of, oh, I hadn't thought of that, but now that you've pointed it out, that's kind of obvious, Mr. Dewick, if I do my job right. Today, we're going to learn the rules to analyze circuits. Kirchoffs laws, named after Kirchhoff, a scientist, a Russian scientist who did a lot of work with circuitry. This is the fundamentals to analyzing a circuit. Kirchoffs laws, there are 2 of them. And they're going to go back to my ski hill analogy. Kirchoffs Current Law, which we can abbreviate as KCL, is basically a conservation of charge. It says that at a junction between 2 wires, between wires, current flow splits or combines and continues to flow downhill. When the current splits or combines, no charge is lost, so that the total flow into the junction equals the total flow out of the junction. Now that sounds terribly confusing. I can see Megan going, say, what? Nope, there it is. Megan, here's what it says. Look up. Suppose you have a circuit and you know that the current is going like this, that it enters from the left and it splits up into two junctions. If you know that this is 6 amps and you know that that's 4 amps, you know exactly how many amps must have gone that way. How many? 2. Skiers don't vanish, if you want my ski hill analogy. The number of skiers on your ski hill, we're not allowed to suddenly have skiers go missing. We're not calling out the search and rescue or anything like that. It's a conservation of charge. What it's really saying is, you know what, those electrons got to go somewhere. Okay? Or if you had, well, let's write this down. The way we write it then is this. We say the sum, there's the symbol for adding everything up, of all the current in has to equal the sum of all the current out. Whatever flows into a junction better equal coming out of the junction. You guys have seen the summation symbol before? If you haven't, it's a great handy shortcut. So, in our ski hill analogy, it means that if 3 skiers converge on an intersection from 2 different paths, then 3 skiers must leave the intersection going downhill. If I have 2 amps coming in this way, 1 amp coming in here, 3 amps going out. And almost always the math will be simple enough that you can do a lot of it in your head. For example, example 1. Remember, this is the symbol for a battery. There's the positive, there's the negative symbol. So the current is flowing this way. Yes, electrons are flowing the other way, and in real life it's electrons that flow, but I'm telling you, for the purposes of us, our current is going clockwise, which you'll often see abbreviated as CW, as opposed to counterclockwise, which you'll often see abbreviated as CCW. Okay. Whenever I'm solving a circuit, really what I want to try and find is the total current, the number of skiers leaving the chairlift, the number of amps leaving the battery. In this case, it's pretty easy to spot because there are no junctions between the chairlift battery and the first resistor, ski hill. How many skiers, how many amps are in this circuit? You're right. What? 1.75. 1.75. How many amps must be right here? 1.75. How many amps must be down at the bottom here? 1.75. By the way, that also means you know the resistance, you know the current through that resistor, 1.75 amps, 1.75 amps, 1.75 amps. If you knew either the voltage or the wattage power or the resistance, you would know the other 2 things. You could now start to analyze this complete circuit. Let's do a bit of a trickier one. Can you tell me the total current leaving the battery? 3 amps? Okay. 0.8 amps apparently went down. How many amps must there be right here? Gotta be. How many amps on the bottom right here? 2.2. Direction. Which way is the current flowing down there? To the right or to the left? Sorry? Left. Right? Follow it through. By the way, this is one of the reasons we defined current to be this way. This allows us to always say that current flows downhill. Kind of like that. What's the current over on the bottom left here? 3. They rejoin. Direction. Left. This is Kirchoffs current rule. Example 2. Show the direction of each current and find the unknown currents. Okay? Almost always my first approach is when I see the battery, I go, hey, current's flowing that way. That's downhill. Can you tell me, can you spot anywhere the total current leaving the battery? Is that obvious anywhere? Can you figure it out? If you can't, that's almost always my first job. So whenever you give me a big messy circuit and I go, well, let's see if I can find the total current. Can you? Why 13 and not 15? All of the skiers are still together. They split up into two groups, but those are the only two groups they split up into. You know what? It's got to be 13 amps starting out. Now that I have that, this is going to fall apart. Let's see. 8 amps went down. That left me 5 amps going this way. Oh, 2 amps split off. How many amps went to the right over here? 3 amps. Follow it through, follow it through. Oh, how many amps down here? Still 3 amps. We meet up again. How many amps right here? 5 amps. Hey, we meet up again. How many amps right here? 13 amps. Here's the battery. That's downhill in this circuit. So I'm now thinking, Dorothy, counterclockwise. Is there any way that we know the total current overall in this circuit? Paige is nodding. Where? They all join together. I guess everybody goes through this ski here. 5 amps. So I'll make a little note. That's 5 amps. Oh, and I think the question now just fell apart. Apparently right here we all shake hands and we say, there's 3 hills, you guys all pick, we'll meet you at the bottom of the next hill. 0.5 amps this way, 2 amps this way. How many amps went to the right? Sorry? 2.5. We all get back together, we go through here. Oh, how many amps went on this left-hand ski hill? 3. When you label your circuit diagram, I don't care about sig figs. I don't care. In fact, by the way, I do give you marks for stuff. So when we're showing work, it's really awkward to list all the steps. It's much more convenient to label our diagrams. So for example, if this was a 7-mark question, this is too easy for it to be a 7-mark written question. But if it was, I would probably say, well, if I see that 3 there, that gets them 1 mark. And oh, if I see that, that gets them 1 mark. So label them, but you don't have to go 3.0 to 2 sig figs. I'm not going to freak out about that. In your final answer is all I'm looking for, accurate sig figs. All right. Hey, that's downhill. All right, ready? I'm going to change things up a little bit. Look up. What's this current right here? Jason? 4.5, because all the skiers got back together, and I do know the total current. What's this current right here? Why? 1 went off. Okay. Let's continue down this particular path. What's this current right here? Also 3.5 amps because the skiers couldn't go anywhere else. Right here is still 3.5 amps because the skiers haven't gone anywhere else, and then they join together. Oh, that I think kind of implies, what's this current right here? 1 amp. Kirchoffs Current Law. Current in equals current out. It's really a conservation of charge. It's saying, look, electrons, are protons that are moving through the circuit even though they don't. Positive charges, current, doesn't vanish. Skiers don't vanish. Now let's get a little more high tech. Let's see if we can actually start to say or predict how skiers will split up. I wrote down here the amount of flow along a particular path from a junction. It depends on the resistance of that path. If the resistor is smaller, more skiers will feel comfortable going on it. If the resistance is higher, skiers are scared. We don't want as many people, no, smaller current. Okay? So, if the resistance of each path leading away from the junction is the same, what do you think you can say about splitting the current? If I have 6 amps leaving the chairlift and each resistor has a resistance R, take a guess. What would make sense for the current? 3 and 3. Sorry? You got it? It might have been a good question. No? Yes? No? Okay. B. Oh, if one path has more resistance, then what can we say? For instance, compare the unknown currents I1 and I2. Big resistance, scary hill. Small resistance, easy hill. We're going to say people are scared, so people will go to the easier hill. Now, I know in a real mountain, it's, oh no, the tougher hills are more popular. The ski hill analogy only carries us so far. So we're going to pretend we have timid skiers. I1 would be bigger than I2. As resistance goes up, current goes down. As resistance goes down, current goes up. By the way, which is why if you have a resistance of near zero, your current is way up. That's a short circuit. That's not good for the battery. Stuff starts to overheat. In fact, we can even be more specific. I'm going to give you this in part C. I hardly ever, in fact never, have to use this, but it's handy to have in your back pocket. You can survive without this. If the currents are simple ratios of each other, we can relate the currents via the same ratios. For instance, find the unknown currents below. The second resistor is twice as big as the first. Twice as big means half as many people, skiers, current. So how can you break a 6 amp current up into half as many, twice as many? Gotta be 4 amps and 2 amps. I don't use that very often to solve a circuit, but that is one of those handy-dandy error checks. Oh, I knew that was going to happen. Hey, my answers look right to me because I noticed there is a ratio between the resistors. That's the current law. There's also Kirchoffs Voltage Law, KVL. And it actually comes out of a conservation of energy. It says that as charges flow around the circuit, they experience voltage gains in the cell and voltage drops across the resistors. For every path through the circuit, the voltage gains equal the voltage losses. Say what? Mathematically, we write it like this. The sum of all the voltage gains equals the sum of all the voltage losses. In my ski hill analogy, Chelsea, here's what it means. If you end up where you started from, whatever height you gained, you must have lost it to get back to the same height as you started from. Or whatever height you lost, you must have gained it back, chairlift, to get back to the same height that you started from. You can't end up in the same spot on a circuit. If you walk a closed loop, if you follow a closed ski hill path and you end up back where you started from, whatever you lost, you must have gained back. It's conservation of energy. So in terms of my ski hill analogy, it says that if the chairlift takes me to the top of the mountain, if I want to get to the bottom of the mountain, I better lose all of my energy back down to zero, all of my voltage back down to zero. It's much easier with an example, example 4. Now I've told you how high the chairlift is. How high is the chairlift? How high is the chairlift? How high is the battery? What's the voltage on the battery, Ben? You gain 20 volts. That means if you start here and you end here, you better lose 20 volts to get here. Okay? So I'll make a little, hey, current's going this way. What's the voltage? Right now I'm at 20 volts. And right here I'm still at 20 volts because I haven't gone down a hill yet. This first resistor, apparently I lose 8 volts. What's my voltage now? Got to be 12. Oh, then I wrote drop equals, I don't know, but what's my voltage have to be at the bottom here? Got to be 0 because I don't have any other ski hills and I get back to the bottom. So how much must I lose through this resistor? You can put a negative, we just don't bother. It's just understood that of resistor, you're always losing voltage, so we got tired of throwing a negative in there all the time. It's a voltage drop. Okay? Next one. Let's even do this, Mr. Dewick. I think I can make these bigger. Yeah, I can. Cool. Still fit them on. Whoop, didn't want to do that. How high is the chairlift? Okay, so right here we're 10 volts. Okay. Now I want you to notice something. Can I, watch. get on the ski hill, shake hands with my friends. Can I go this way and end up at the bottom? Yeah, I didn't go uphill at all, right? I went downhill the whole time. So if I start out 10 volts high, I end up 0 volts high, and I only go through one ski hill, what must this voltage drop be? I must lose 10 volts. It's 10 volts right here, 0 volts right there. But not only that. Could I go through that path there? Could we shake hands and meet up? Oh, okay. How many volts must this resistor lose? Also, 10 volts. Because that's a legitimate ski hill path. Wait a minute, Mr. Dewick, that's a total of 20. No, it's not a total of 20 volts. It's the voltage law says, doesn't matter if you split up, it's the height changes have to match up. 10 volts at the top, 0 volts at the bottom. Let's try a couple more. Example 5. All right. 12 volts. All of us right now, all of the skiers are skiing together. So they all go through this first resistor. When they go through this first resistor, what's their voltage right here? 4 volts. In fact, what's the voltage right here? We're at 4 volts. Can I get back down to the chairlift of 0 going that way? Then how high must this, what's the voltage drop in this resistor ski hill? It's got to be 4 volts to get to 0. Oh, can I go this way as well? Now also think about it. We're all skiing together. We shake hands. We split up. We meet up here. We must have gone through the same change in height. Otherwise, we couldn't meet up at the bottom. Right? So this must also be a 4 volt drop. 4 volts to 0. Ooh, let's do one with multiple resistors. More than one ski hill when we split up. Let's see. How high is the chairlift? 60 volts. So right here, we're still at 60 volts. Oh, we all go down the first resistor. We all lose 15 volts. We're at 45. Right? How high is this one hill, this section, this path? How high is it? It tells me 18 volts. Can we shake hands and meet up right there? How high must that path also be then? Got to be a total of 18 volts. Has to be. Otherwise, we couldn't meet up again. So, oops, I didn't want to erase that 5. If that's 10 volts, how high must that hill be? It's got to be 8 volts. Otherwise, I can't also go down a total of 18 volts and meet up with you guys again. So for what it's worth, I also know that right here I'm at 35 volts technically because I've gone from 45 through a 10 volt drop to 35, through an 8 volt drop to 20 what? 27 volts, and this is 27 volts. We meet up here. Oh, we all go through the final hill. We have to get to the bottom of the chairlift, otherwise we got an incorrect or a short circuit. What must the voltage drop be in that final resistor? Got to be 27. Got to be. By the way, when I'm solving circuits, I only fill in the resistors. I don't fill in the top and bottom. It gets too confusing. Just, we'll get there. Note, there are really 2 useful conclusions to draw from Kirchoffs Current Law. Sorry, I keep meaning to correct this, from Kirchoffs Voltage Law. The first one is this. For any complete loop around the circuit, if you end up back where you started from, the voltage drops equals the voltage gains. Whatever height you lost, you better gain back, otherwise you can't get back at the same height. And second, no matter which pathway you choose, whether you go this way or That way, the total voltage drop between those two must be the same if you leave together and you join together. If you split up and you meet up, you better all go through the same voltage drop. I'm really done the unit. The rest of this is just going to be applying this to Ohm's law and Joule's law. Oh, okay. My friend who typed this up, he says, to see the voltage relationships, it's sometimes helpful at first to redraw the circuit so that all resistors are pointing downhill. For example, consider the previous circuit. You could, if you wanted to, really flog the ski hill analogy to death. You could say, here's my chairlift. Everyone goes down the first hill, shake hands and split up, meet up at the bottom. Okay, or 5B could be redrawn as chairlift. Everyone goes through there, split up. You guys are going to go down one big hill. We're going to go down two smaller hills. We're all going to meet up. We're all going to go down that. I'm not going to advise doing that just because I'm lazy. I won't do that. You can if you want to. I'm going to encourage you, just get used to analyzing the circuit diagrams. What I always do is just that, and that I can kind of clue in. Instead of thinking downhill, I rotate through clockwise or counterclockwise. Example 6 says, write equations relating the voltage drops. Well, let's see. In the above circuits, in A, where am I going here, Mr. Dewick? We're going to come back to that. Instead, we're going to go to example 7. If there are several resistors along a path, the charges will lose a fraction of their voltage energy in each. Example 7. If you have two equal resistors along a path, what can be said about the voltage drops? For instance, find the voltage drops in the circuits below. What would make sense if you go through the same size resistors and you have 30 volts to start out? Each one's 15? Convince me. You gonna make it? He needs your help.
Wake up.
Convince me. Ready? I'll prove it. Do you agree with me that both of these have exactly the same current because all the skiers go through both? So, yes? And the question says they both have the same resistance? Yes? Well, if V equals I times R, and I is the same, and R is the same, what can you say about V? It's got to be the same for both of them. Therefore, V is the same. And the only way I can get an identical voltage is 15 apiece. So, 15 volts, 15 volts. If the resistances are not the same, then what can we say about the division of voltage? Well, again, it's the same current for all of them because the skiers go through all of them. Yes? Okay. So if V equals I times R and I is the same, if you have a big resistance, what would happen to your voltage answer? Bigger. If you have a small resistance, because I is the same, what would happen to your voltage answer? I said a big resistance was like a really scary hill. It's got a bigger drop. It uses a bigger voltage. That's why people are scared of it. It's got a bigger, if you're looking for a way to remember this. Oh, big resistance, going to use more voltage because it's a scarier drop. If they are simple ratios of each other, we can relate the voltage drops via the same ratios. For instance, find the voltage drops below if you know the first resistor is twice as big as the second. So if the resistor is bigger, we said that the voltage is bigger. If it's twice as big, you know what? It's going to be 20 volts and 10 volts if I'm dealing with 30 volts. It's the only way I can do a twice as big split. You can survive perfectly well without having part C in your brain. It's a nice handy built-in error check. I think in the homework, he'll give you a couple of questions where you need to use this trick, but I won't on a test or a quiz. Although it's helpful at first to label the voltages at each point in the circuit, we're going to stop. We're now only going to label battery and resistors, nothing else. So, boys and girls, let's analyze our first circuit. Example 8 says, find the unknown voltage drops and currents and resistances by using V equals I times R. And the hint I have for you is if you know 2, you know 3. In fact, if they start talking about power, because power is VI, if you know any 2, you know 4 things. What did I say we always try and bend our efforts towards finding first, if at all possible? Total current. So look at the battery. How many skiers are coming off the chairlifts? Can I figure that out? What the current total is? What? Oh. No, that's the voltage.
4.
Strike 1, strike 2. Please hit it out of the park, Josh. What? Oh, it looks like every skier goes down that one, and it's 4 amps. So I'm going to make a little note here. Hey, I got 4 amps. There's my total current. Oh, and I'm going to do that. That's downhill. Do I know 2? Oh, then I actually know 3. What's the resistance here? Well, if V equals I times R, I guess R equals V over I. Right? What is 1.5 ohms? Okay. We go this way, that way. 3 amps. Oh. How many volts high must this hill be? Here's your hint. That's a closed loop.
18.
Can't be 18.
Full.
Got to be 12, because you already used up 6. See it? Do I know 2? I know 4 things, although I'm not asking for power. Do I know 2? I can certainly tell you the resistance. How many ohms must this resistor be? Hey, I can do this in my head. 12, it's 4 ohms. Cool. You didn't tell me anything over on the right, Mr. Dewick. Oh, what's the current in the right-hand one?
1.
Got to be 1 amp. Also, is that a legitimate ski hill path closed? Oh, what's the voltage drop have to be in that one? Also, it turns out to be 12 volts. And now I can tell you the resistance in your head, 12 divided by 1. 12 ohms. Did we fill in everything? Yep, we got everything. Mr. Dewick, what's the resistance of the battery? Ideally 0. In real life, not, but we'll talk about that later on. Ideally, you want no resistance in your battery, though. B. Current's going that way. That's downhill. Can you tell me the total current running through this circuit, the total number of skiers on the ski hill?
2.5.
Where'd you get the 2.5? Oh! 1.5 went that way, 1 went that way, and they were initially all together. I guess we got 2.5 amps going through this ski hill. So now let's start walking along the hill. 21 volts in that first resistor. What's the current in that first resistor? 2.5 amps. What's the resistance of this first resistor? Whatever the heck 21 divided by 2.5 is. 8.4. What's this middle voltage have to be? How'd you get that? Oh, starting 35 high, we lose 21 on the first hill. We get down to the bottom of the chairlift going through this hill. Better be 14 volts. Oh, and I guess the resistance then is V over I, also 14 ohms, because it's 14 divided by 1. That's kind of nice. What's the voltage over here on the right?
14.
Also 14 volts, it turns out. And what's the resistor? Whatever the heck 14 divided by 1.5 is. I think this is going to be repeating. Yeah, 9.3 ohms. This is kind of fun, Mr. Do-It. You know what? I kind of like these as little puzzle brain teasers, to be honest. It's like a crossword puzzle, sort of. C. Going this way. How much more are we doing here? Yeah, nearly done. Can you tell me the total number of... Ooh. Not yet. Okay. So, I told you my first goal was to always try and see if I can figure out total current. If not, my next is I go and see, is there any resistor anywhere where I know two things? Because if I know two, I know four things. Well, three today, but is there any resistor? What? Oh, that one? Okay. Let's see. What's the resistor here? 35 ohms. Does that help me? Well, let's look at this guy. Can I walk a closed path like that? Yeah? What must this voltage be? Got to be 5, right? Because it's 5, 35, there's my 40. Oh! What's this voltage have to be?
35.
Jake, do I know 2? I know 3. What's the current? Oh, what's the total current in this circuit? I think now I know. I got all the skiers on all the subhills. 8 amps. And I can put 8 amps in this first one here. And now I can tell you the resistance. It's going to be 5 divided by 8. 0.625. These little puzzles. Okay? Try and find total current. If you can't, go hunting at resistor. Go hunting at stuff that you know 2 of, because you know 3. And then start walking closed paths. That's your third strategy. Start walking ski hills. Current's going this way. Do you know total current? I do? What? I do. 5 amps, because they gave me the first ski hill, and everyone goes through that one. So 5 amps. By the way, you'll find once you have total current, almost always these start to fall apart. Let's see. What can I fill in now? Oh, can I say that? Everyone goes through that last hill. Yes? Do I now know 2 in that last hill? Then I know 3. V equals I times R. Hey, I can do this in my head. 5 times 4. You know how high that hill is? 20 volts. How high did we start out, by the way? 70. Oh! Is that a closed ski hill path? Do I know every hill but one? How high is the chairlift? 70. How high is that middle hill? 15. How high is the bottom hill? 20. How high is the first hill have to be? What's the voltage of the first hill? Got to be, is it 35? Do I know 2? I now know 3. What's the resistance?
7.
Oh, by the way, that middle hill, I could have jumped to that sooner because I know 2 things there. That current is not a mystery to me. What's the current in the middle hill? I know the voltage is 15. I know the resistance is 5. I equals V over R, right? 3, sorry, 3,
Yeah.
Mr. Duick. What was I going? 3. Hey, what was our total current?
5.
How many went down this hill? 3. How many went down the right-hand hill? Must have. Oh, hey, look. Taylor, can we shake hands and meet up right there? Well, if this hill is 15 volts high, how high must this hill be if we can go down one ski hill and meet up? Got to be 15. Oh! Now I know the resistance. Resistance is not futile. 15 divided by 2. Ta-da! The circuit is solved. E. There's a bit of a glitch. This line should actually be right there, and then there's a resistor right after it. So kind of pretend that that's not there. And that, anyways, sorry. The point is this. This time the current is going that way. Okay. Well, how high is our chairlift? 32. Do I know total current anywhere? In fact, do I know any current anywhere? Not yet. Okay. There's a couple of, I know 2. So I know the, what is the current in this bottom left resistor then? I think current is voltage divided by resistance, isn't it? Okay. Ta-da! Now I know total current, by the way. It is 4 amps. They're going to split up. Some go this way, some go that way. So it's not going to be 4 amps in either one. Now I start walking ski hills. How high is our chairlift? 32. How high is the first ski hill that we go through? 8. So, how high is this hill?
24.
Got to be 24 since there's no other ski hills and I can get back down to the bottom. Right? Oh, do I not know 2? Then I know 3. What's the current there? Got to be 2.4 amps. And since we started out with 4 amps and 2.4 amps went this way, how many amps went this way? Got to be 1.6 amps. Got to be 1.6 amps. Right? Oh.
If that's 2.4, the first one should be 0.25.
The first one should be 0.25. I have no idea what you're talking about.
How do you get 2.4 on the second?
Here?
Yeah.
V divided by R,
Okay. Okay, never mind.
right?
Sorry.
It's okay. No, it's a good question. You ask good questions, usually. Mabad, can we shake hands and meet up there?
Yeah.
Then if this one hill is 24 volts high, what must both of these hills be in grand total?
24.
24 volts high. How high is the bottom hill? 10 volts. How high must this hill be then?
14.
Got to be 14. Do I know 2? I know 3. Resistance is going to be 14 divided by 1.6. That one I'm... Sorry? 8.75? And what about the top resistor? It's going to be 10 divided by 1.6. 6.25? And I said amps. I meant to put ohms in that bottom one. Let's fix that, Mr. Duke. Is that okay? It's Kirchoffs laws, only two. But this is the fundamentals of solving any circuit out there. You know, a nice way to test understanding is light bulb questions, because light bulb questions allow us to bring in power, VI. Because the more power, the brighter the bulb. The less power, the dimmer the bulb. And so a great way to ask you a question is to ask, hey, if I change this, will a light bulb be brighter or dimmer? Those are, hint, hint, very good using principles of physics right to explain questions. Hint, hint, hint. So, the bulbs below are identical. In example 9, same resistance. Oh yeah, turn the page. Which bulb is brighter? Well, let's see. Why can I do this? Why do they both have 10 volts? Why do they both lose 10 volts? Because you can either, Jason, ski this ski hill, gain 10 volts from the chairlift battery, lose 10 volts, or you could ski that ski hill. They both got to be 10 volts apiece. So, I'm going to make a little note here. Right? What can you tell me about their resistance? The question says it's the same. And do you recall we said that power, it was VI, but it was also V squared over R. That was the third version of Joule's law that I gave you last day. So if the voltage is the same, and the resistance is the same, and the brightness is really how much power, what can you tell me about their brightness? What can you tell me about their power? Oh, let's even put a therefore like it's a proof. So same brightness. Okay. If you hooked up two identical flashlight batteries in what we call a parallel circuit to the same, two flashlight bulbs in what we call a parallel circuit to the same battery, they'd have the same brightness. What if instead of hooking them up in parallel, what if you hook them up in series, one after the other? Like this one. Well, I know that they have the same resistance, yes? What can you tell me about the current going through each of those bulbs? If the current is the same, and the resistance is the same, and V equals I times R, what can you tell me about the voltage drop in each of those bulbs? In fact, not only the same, I can be more specific. Gotta be. So, power equals VI, that was our original Joule's law. If the voltage is the same and the current is the same, what can you tell me about the power? What can you tell me about the brightness? Really?
Same.
Oh, yeah, come on. Hey, what if I made one bulb twice the resistance? Can you see, you could probably, twice the resistance would make, this is a bit yucky, but what would twice the resistance be? 6.66666 repeating for one voltage and 3.333. This is a yucky one. You really want one that divides by 3. But then you can walk through and figure out which one is brighter, which one is dimmer. Homework for Wednesday. Need to practice this. This is fundamental. Number 1 is good. Number 2 is good. Number 3 is good. Number 4 is good. 5, there's a more challenging light bulb question, but I've tried to model for you how I would approach solving these. Six is good. 7 is good. Yeah. 8 is good. Just do it. These are, by the way, your goal is to get, so each one of these takes you about 30 to 60 seconds, because you'll notice we're doing almost all the math in our heads, the odd dividing on our calculator, but the math here is not the big concept. The concept is the concept. Skip number 9. Oh, 10's got a nice little one there. That's kind of fun looking. Sure, 11 looks good. You got total current. That falls apart pretty quick. $12. So 14, 15, and 16 are using those ratios. I'm not going to assign those. I gave you the ratio trick. You can survive without it. Sounds like a lot. Maybe it is. I don't know. But there you are. Kirchoffs laws.